Hello everyone, this video is intended to be a second example after you've already been introduced to the idea of ice tables in general. The year I'm recording this, I linked a different video made by someone else. I want to watch that one first, but I just wanted to go through one more example with you. And in this type of problem, it's going to be the type of problem where we are given one of the equilibrium concentrations of one of the species, which makes a pretty big difference in how the problem should be approached. So let's get right to it. So I'm going to look at this particular page in the workbook, and I'm going to do problem 2 here. So what I have done on another page is I've broken things out a little bit. So a scientist is mixing hydrogen gas and fluorine gas to produce gaseous hydrogen fluoride. So the first thing I have to do is write that equation, but it's not too bad, and I've done that up above. And then it says she introduces this many moles of hydrogen and the fluorine and the hydrogen fluoride. So we do have all three species present initially. So it's important to read every word and really pay attention to these. And it's a 1, so we want to put concentrations in ice tables, but the volume is 1, so we don't need to worry about that because the concentration and the number of moles is going to be the same since the volume is 1. And then super key word here, at equilibrium. So we are given one of the equilibrium concentrations, and it's 0.189. So I have written out the equation up here, and you may want to pause the video and get this all kind of sketched out, but there we have the equation, and we got hydrogen and fluorine and HF. So the first thing I'm going to do is go ahead and put in the initial concentrations that I was given. Now unfortunately, at the moment I'm doing this, my pen is broken, so I'm going to have to write this with my mouse, so it's going to be a little sloppier and slower. But we started off with this many moles, but again, that's also the concentration. So do pay attention to the volume of the container, but since the volume of the container is 1, we can just go ahead and put the moles right in here. And then the initial concentration of HF. Okay. So I am also given a concentration of the hydrogen fluoride at equilibrium. And again, that's key. That's going to make this problem different to solve than some other ones we're going to do where we won't know any of the equilibrium concentrations. But it tells us it's this. Now, again, at least the year that I'm making this right now, I linked a different video. I'm going to take a slightly different approach than the person who made the video did. What I'm going to say to myself is this. So the change is apparent here. If I just look and I do some math and I subtract these two, this must have gone up, so it's an increase of 0.0089. So it went up by that much. Now one thing that's always going to be true of the change line is it's always going to fall in line with the mole ratio, which is 1 to 1 to 2. So however much this went up by, first of all, these are decreasing, so I know that's a decrease. And however much this went up by, those must have decreased by half as much because of the 1 to 2 mole ratio. So I'm going to divide this number by 2, and 0.0089 divided by 2 is 0.0045. 445 rather. Squeeze in another 4 there. 0.00445. And again, I'm doing that just to keep things in line with the mole ratio. It's 1 to 1 to 2. These are going down. The product is going up. And there I've got all my changes. And then once I have that kind of penciled in, I can just do the actual subtraction here. So I'm going to go 0.0350, and it's going to go down by that much. And it's 0.0306 at equilibrium, and then 0.0623. So basically, I'm just taking advantage of, I know exactly how much this one went up by, and I can take advantage of the 1 to 1 to 2 mole ratio. You got to have less product to make the less reactant if you're going to make the product, so these must have went down. My change line, as I said, is 1 to 1 to 2, just like the mole ratio, and then from there I can just do the simple arithmetic of this minus this, this minus this, and then this plus this was already there. So that is by far the hard part, but the question ultimately asks us, well, it says calculate the equilibrium concentration of all species, which we've done. The unit would be mole per cubic decimeter. If, you actually had to put the answer, you'd want to put a unit there, of course. And value of Kc under these conditions. Okay, well, the equilibrium expression, product's on top, so it'd be HF. And then we're going to square that. Of course, this is an equal sign that I'm missing here. And then H2 over F2. And then we're going to go ahead and substitute the actual values, the actual equilibrium values that we got there. So it's 0.0189. Don't forget to square it. Over 0.0306 times 0.0623, and then all of that, I do believe, equals 0.0187. So there we have it for this problem. Thanks for watching. Try some of the others on this page. All of the ones on this page are of similar, where we're given one of the values at equilibrium. So give those a shot. Thanks for watching, and we'll see you next time.